Problem 2 on this exam describes what should be clear is a ballistic or projectile motion problem. You launch a rock horizontally. The fact that it says horizontally means, hey, this makes it easier than if you were launching at some arbitrary angle, initial angle theta, and had to worry about the components of the initial velocity. So this makes the problem easier. There's no vertical component to the initial velocity. It's all horizontal. Okay. You're told the distance horizontally it has to travel is 5,000 meters. Happens to be north, but the important thing is this is horizontal. And you're told the vertical component of the motion is 1,300 meters down beneath the rim. You're also given the mass of the rock, but this is actually a red herring. You should remember from our discussion of projectile motion that mass didn't enter into anything. It's only when we get to Newton's laws that the mass enters, as long as we're ignoring air resistance, which we're told to do. So we need to calculate how long it takes the rock to reach the river, how fast, and what's its velocity when it does land. And these questions are actually asked in the order that makes it easiest to solve the problem. So let's get started. Okay, 2A. The first thing you should recognize is that the time in the air depends only on the vertical component. Time in air, t, depends only on vertical component, y hat component. Now you don't have to write this on your exam. It should be obvious from your work that you understand this. Let me just draw a coordinate system because I do want to define my y as up or down. In this case, I'll pick it as up, but that's arbitrary. That's not required. So how are we going to solve for the time in the air given the parameters that we're given? Okay, and we have 4 equations that we can use for constant acceleration, which is true in this y direction. And if you look at them and think about them, you should end up focusing on this one. Y equals y naught plus v naught yt plus 1/2 a sub y t squared. Because this says the parameter you want, time, and it's got other things that you know. You know the distance it falls, y minus y naught. You know the initial velocity, okay, is in the y direction is 0 because you've launched it horizontally, and you know the acceleration of gravity, or the acceleration is the acceleration of gravity is y. So this equation reduces to y minus y naught. If I take the y naught to the other side, notice this is just delta y, final minus initial, is equal to v naught yt, but that's 0, so I ignore that. And this term becomes negative 1/2 gt squared. Okay, and I can solve this pretty easily for t. Let me just do that here. T is equal to, multiply both sides by 2 over g, or negative 2 over g. So it's negative 2 delta y divided by g square root. You may get worried for a second that this is a negative sign in the square root, but remember delta y will also be negative because I picked positive up and it's going to land below the initial height. So all you have to do now is actually plug in the values. The square root of 2, or negative 2, I guess, times negative 1,300 meters divided by 9.81 meters per second squared. Pull out my calculator, which uses reverse Polish notation. So it may look a little odd to you. 2 times 1,300 divided by 9.81 square root equals 16.3. If I want to keep 3 significant figures, units will be second. The meters cancel out. 1 over second squared becomes second squared. Square root becomes seconds. And don't forget to circle your answer. Okay, B. B, now we want to find how fast you have to launch the rock in order to hit the river. We've already used our vertical component to find the time in the air. And to find out how fast you have to launch it, remember it's a complete horizontal launch. The horizontal motion is described by x equals x naught plus v naught xt. So we know how far it has to travel, x minus x naught. We know the time, and so we can solve pretty easily for v naught x. And realize that v naught x doesn't change, vx doesn't change. The velocity at any moment in the horizontal direction equals the original velocity. Or V naught x is the same as Vx anytime. So that's just equal to delta x over the time, or delta t if you like, 5,000 meters horizontally in 16.3 seconds. Calculator, 5,000, enter 16.3 divided by, and we see that the velocity in the x direction, which is the velocity you need to launch at, is 307 meters per second. Okay, which brings us then to part C. In part C, we're asked to find the velocity when the rock lands in the river, when it hits the river, in magnitude and angle in degrees below horizontal. Well, it's easy to start with the velocity in the x direction because we know that's constant, 307 meters per second. So to determine the velocity in terms of components, this is horizontal, of course, all we need is an expression for Vy, but from your constant acceleration equations, one will tell you, or just your understanding of velocity and acceleration, Vy and V sub y will be the original velocity in the y direction plus the acceleration in the y direction times time. The original velocity in the y direction is 0, because you launch horizontally. The acceleration in the y direction, minus 9.81 meters per second squared. Time is 16.3 seconds. Okay, plug these in. 9.81, enter. 16.3 times. And you see you've got 159.9, or V sub y equals 160 meters per second. Now, in principle, these two values, the x and y components, tell you the velocity, but in this case, the problem says no, you must supply it in terms of magnitude and direction. So while you've got v sub x component and v sub y component, when the rock hits the river, we want the magnitude v and the angle below horizontal. By the way, if you want, you can say v sub x is v sub north. That's fine. I'm just not bothering to specify that here. So in any case, how do we get the magnitude of v? That's just the square root of vx squared plus vy squared, or the square root of 307 squared plus 160 squared. So 307 x squared, 160 x squared plus square root equals 346 meters per second. You should always think about these things. It's a little bit bigger than the horizontal component, which is good. That's what you'd expect, because the bigger of these two values should dominate when you do the square root of the sums of the squares. How about this angle theta? That's just the arc whose tangent is Vy over Vx over, or the arc whose tangent is 160 divided by 307. 160 divided by 307. Oops, sorry, 160, 307 divided by the arc tangent is 27.5 degrees. Circle your answer and you're done with this problem.